In one of the last videos, we learned about some of the special parallelograms like rhombuses, rectangles, and squares, and we learned what the qualities of those special parallelograms were. In today's video, we're going to be looking at how we could prove that a certain parallelogram would have to be a rhombus, or would have to be a rectangle, or would have to be a square based on some information that we know about it. So let's jump right in and take a look at our first theorem. So this theorem is actually the converse of a previous theorem. Previously we learned that we had a theorem that said if a parallelogram is a rhombus, then its diagonals are perpendicular bisectors of each other. So this one says if the diagonals of a parallelogram are perpendicular, then the parallelogram must be a rhombus. So just to recall, the definition of what a rhombus is a parallelogram with all congruent sides, with 4 congruent sides. So the question we have to ask ourselves is, why is it that if we know two things about this shape, we know that it's a parallelogram and we know that its diagonals are perpendicular, how does that make it so that the 4 sides must all be congruent, make it so that it fits the definition of a rhombus? So that's what we're going to take a look at. We're going to prove why this will always be true, that if you have a parallelogram where the diagonals are perpendicular, then all 4 sides of it must be congruent and it therefore must be a rhombus. So what we're going to do is we're going to look at the fact that we already know that it's a parallelogram. And in every parallelogram, the diagonals bisect each other. So that would indicate that in this picture, I'm going to label this point here, point X, this intersection of my 2 diagonals. I would know that segment JX and segment XL are congruent, and then segment KX and segment XM are congruent. I also see that I have perpendicular diagonals, which means that all 4 of the angles here are all right angles. So if I look at the 4 triangles in this picture, I notice that they all have right angles in the middle, and then I notice that they all use this side as one of their sides, or this side, right? These either segment XJ or segment XL, which are the same length, is used as a side in each triangle. And then we can say the same thing about segment XK and segment XM. They're the same length, and one of them is used as a side in every triangle in this picture. So what that means is that triangles JXK and LXK and triangle LXM and triangle JXM are all congruent by side, angle, side. All 4 of those triangles have 2 sides that are congruent, and then the included angle, which would be the 90-degree angle in each of them, they're congruent. So that means that all 4 of these triangles are congruent to each other by SAS. Well, once we know that these triangles are congruent because of these 3 parts, we would also know that their other parts are congruent. Specifically, we would know that segment JM, segment JK, segment KL, segment LM are all the same length. So we can say, therefore, segment JK is congruent to segment LK, is congruent to segment LM, and is congruent to segment MJ because of what we call CPCTC, that the corresponding parts of these congruent triangles must be congruent. And if all 4 of those sides are congruent, then again, that makes this a rhombus. So that's our proof of why if we have a parallelogram with perpendicular diagonals, it must be a rhombus. It must have 4 congruent sides. This next theorem is another way that we could prove that a shape would have to be a rhombus. So what we have here is we have a theorem that says that if one diagonal bisects 2 angles of our parallelogram, then that parallelogram must be a rhombus. So you can see we have segment BD bisecting angle ABC and angle CDA. And this is a parallelogram because we can see that the opposite sides are parallel. So the question is, when that happens, when this diagonal bisects these 2 angles, why does that mean that all 4 sides of this shape must be congruent? Well, let's take a look for a second. First of all, we notice that since it's a parallelogram, these two sides would be congruent, and these two sides would be congruent. So let me go ahead and mark segment BC congruent to segment AD, and segment CD congruent to segment AB. Right? I'm gonna write that out. Since ABCD is a parallelogram, segment BC must be congruent to segment AD, and segment AB must be congruent to segment CD. And that's because in every parallelogram, the opposite sides will be congruent. But then we notice that angle ABD is congruent to angle ADB. ABD, this angle here, is congruent to this one. So triangle ABD must be isosceles. All right, so I'm going to write that out. We got a lot of writing on this proof. Let's do it this way. Let's say that triangle ABD is isosceles because angle ABD is congruent to angle ADB. So that means that segment AB is congruent to segment AD. Okay, so follow where we're at. We've decided that actually these two segments must be congruent because these two angles are congruent. ABD is an isosceles triangle because these two angles are congruent, meaning that the two sides across them must be congruent. So now we can actually modify and say that that must be the mark that I have on segment AD. It must be the same mark as I have over here. But then if AD has that mark, then that means BC also has that mark. All right? So now I can see, look, all four sides are the same length. All right, so let me kind of finish my proof over here. This means, I'll say, this means that AB is congruent to AD, which is congruent to BC, which is congruent to CD. All four sides are congruent, and ABCD must be a rhombus. So that's our proof of why if this diagonal bisects these two angles, this shape must be a rhombus. In this final theorem for the video, we're looking at the way that one way that we could prove that a parallelogram must be a rectangle. Okay? So again, we have this parallelogram here, the opposite sides are parallel, and we're going to say that the diagonals are congruent. XZ is congruent to WY. Why does that mean that this must be a rectangle, meaning that all of these angles here, WXY, XYZ, YZW, and ZWX, why are those all 90-degree angles just because this is a parallelogram and these diagonals are congruent? Well, let's take a look here. I'm going to look at triangle XYZ and triangle WYZ. Okay, I'm going to look at these two triangles. I got a triangle right here, and I got a triangle right here. In those two triangles, I know that XY is congruent to WZ, because if this is a parallelogram, these opposite sides have to be congruent. So segment XY is congruent to segment WZ. And then I also know that segment XZ, it says, is congruent to segment WY. That's part of our kind of given information right here. Third, I know that both of those triangles use segment YZ, so I'm going to say that it's congruent to itself. Now that all put together tells me that triangle XYZ is congruent to triangle WZY because of side, side, side. So now again, I have these two triangles that are congruent. I'll kind of outline them. One of them I'll outline in green, and then the other one I'll outline in yellow, just so you can kind of see the two triangles that I'm talking about here. Okay, these two triangles must be congruent. And if those two triangles are congruent, then angle XYZ must be congruent to angle WZY. But, so that's these two angles right here. These two angles here and here are congruent by CPCTC. So I'll put that out there. by CP, CTC, because they're corresponding parts of two triangles that we just said are congruent, so they must be congruent to each other. I also know that this segment and this segment are parallel, again, because we said that this was a parallelogram, so these opposite sides of it are parallel. That means that these two angles, not only are they congruent, they must also be supplementary. So angle XYZ is supplementary to angle WZY because they're same side interior angles, because they are same side interior angles, and I have parallel lines. So the same side interior angles have to be supplementary when I have parallel lines crossed by a transversal right here. So not only are these congruent to each other, they're also supplementary, which means they add up to 180. And that would tell me that the measure of angle XYZ and the measure of angle WZY would have to both be 90. And now, if this is a 90-degree angle and this is a 90-degree angle and this is a parallelogram, that means this and this, those two angles have to be congruent. So I have a 90-degree angle there, and then the same thing could be said about angle XWZ. So we can now say that, that the measure of angle WZY must be equal to the measure of angle WXY, so that's a 90-degree angle. And we can say that the measure of angle XYZ must be equal to the measure of angle XWZ, so that has to be a 90-degree angle. And, well, there we go. All these angles are 90 degrees, and so that must be a rectangle. Now, one thing to keep in mind is we also talked before about squares. We talked about how a square has all the properties of a rhombus and it has all the properties of a rectangle. So what that would indicate is that if you want to prove something is a square, you must prove that it is both a rhombus and a rectangle. So to kind of finish this statement, if you can prove that a parallelogram is both a rhombus and a rectangle, then it must be a square. It must be a square. So if you want to prove that something is a square, you got to be able to prove that it's a rectangle, that it has four 90-degree angles, maybe because its diagonals are congruent. And you would have to prove that it's a rhombus, maybe because either the diagonals are perpendicular or because the diagonals are bisecting each diagonal is bisecting two angles of the parallelogram. Do both those things and then you can say, oh, that must be a square.